So sorry for the delay. Okay. So now can you hear us well?
Yes, it's okay.
Okay. So Anton, please continue.
So I will make a short recap. We are research unit plasma technology, and we are focusing on plasma engineering, more specifically on atmospheric pressure plasmas. Then we are dealing with design of plasma sources, which are coupled with the study of plasma physics of plasma surface interactions, plasma liquid interactions, and also recently with the study of plasma physics of processes during the gas reforming and gas treatment. And all of this is coupled also with plasma diagnostics. This is my main field of expertise. where we are working on emission spectroscopy and imaging. We are developing different methods for electrical field measurements and voltage current measurements and nanosecond discharges. And also we are working on laser spectroscopy and rare environment scattering. This is our team. 2 years ago, now we have about 25 people, 25 students, and for permanent staff working in the group. So what do we mean by cold plasmas? Cold plasmas are typically plasmas where electron temperature is in the range of a couple of electron volts, and gas temperature is typically below 3000 degrees. And if you look on the diagram of electron temperature, gas temperature, then cold plasmas are typically in the area which is covered here with purple color. Those kind of plasmas are usually very non-equilibrium, and they have a rather low degree of ionization. And very important, they are very chemically active. And this is specifically the reason for us to study those kind of plasmas. We want to initiate different chemical processes with the use of plasma because of possibility to ignite or to initiate processes at relatively low temperature where they can be initiated by electrons or is by electron impact. So we can initiate chemical reactions, and some of them can be initiated even below thermodynamic limit. What does it mean? If we look on a classical Arrhenius equation, there we will have the part of the energy which is provided by plasma, and it helps to reduce activation energy of reactions. So in principle, some reactions can be started at a very low gas temperature, and you don't need to have overheating of the gas to reach thermodynamic limit. And one of the examples, which is already 150 years old, and probably one of the first and very successful examples of kind of non-thermal plasmas and plasma chemistry initiated by such kind of plasmas, is a process which was developed by Siemens for ozone formation. And you can find plenty of other chemical processes which are now initiated by plasma in different books, including the book of Friedman and also the one which is indicated here. However, there are problems with cold atmospheric pressure plasmas, and one of the problems is related to very high frequency of collisions. We are working with atmospheric pressure. There are multiple collisions between particles that leads to the constriction of the discharge and thermalization. So basically, if we have a corona discharge which we want to use for treatment of gas, if we increase power, what we inject in corona discharge, typically what is happening, we are forming a spark. And spark forming a thermal plasma, we have the losses of energy on gas heating, which is not very efficient to do by plasma. And we immediately move from non-thermal plasma into thermal mode, and initiation of chemical process in such kind of plasmas is not very energy efficient. What we want to stabilize discharge. So we want to have discharge which is diffuse, where we can treat large volumes of gas or large materials, large samples in the plasma, and we would like to avoid thermalization. And for that, in our group, we are working on stabilization by fast-flowing discharges, by pulse excitation, dielectric barrier discharges, also microelectrodes and plasma jets. And I will give you 3 examples today of processes which we are trying to develop by working in non-thermal plasmas. And the first one was a project which we will dealing with for 5 years on nitrogen fixation. The idea was to somehow solve, or at least try to provide solutions to solve the problem in a chemical industry with growing of CO2 content, which is related to the change of the climate. And what we want to do, we want at least somehow help to electrify the industry. And the process, what we are targeting is a Haber-Bosch process, which is very known for nitrogen fixation. It's the main process which is currently used to produce fertilizers. And it is based on the use of catalysts at high temperature and high pressure, when ammonia can be produced rather efficient with energy cost of about half megajoule per mole. Unfortunately, the process itself is very energy demanding. It consumes about 2% of all the electricity or all the energy which is produced in the world. And also it is responsible for about 300 million metric tons of CO2 emission. And the process itself is optimized, very well developed in the industry and profitable, but unfortunately on very large scales. So what we were trying to do in our lab, we were trying to find the possibility to run either this chemical process or formation of nitrogen oxides by the use of plasma. And for that, we were looking for two pathways. One of them, the oxidation pathway. With the use of plasma, we want to produce nitrogen oxides. And the second pathway is a reduction pathway where we can generate ammonia. And the basic idea is that you can do it by two mechanisms. One of them, because of direct electron impact, you can dissociate nitrogen. And then used by the atomic mechanism, you can produce nitrogen oxide. However, this process will require electrons of about 9.78 volt, which is a lot of energy you need to give to break the molecule of nitrogen. The second one is vibrational excitation, where you first vibrationally excite nitrogen, and then nitrogen or oxygen, which also can be vibrationally excited, will react in the next step, forming nitrogen oxides, but through the Deutsch vibrational pathway. So you don't need to provide immediately 9.7 electron volt in one electron impact collision. You can do it step by step to increase the energy, vibrational energy of nitrogen molecule and then to break it. And of course, this process is much more energy efficient than the first one. So what is our plasma system? We have a nanosecond pulse discharge, which was generated between metal pin and the surface of liquid. So the plasma was ignited between metal electrode and liquid electrode. The pulse duration in this plasma was about 10 nanoseconds. And the reason for this kind of short pulses was the following. You have duration of pulse so short that plasma has no time to transfer from non-thermal plasma into thermal. So plasma has no time to form cathode spot on one of the electrons, as on liquid electrode or high voltage electrode. So plasma exists in non-thermal conditions. And because it has no time to transfer to thermal discharge, we hope that we can initiate oxidation processes and we can break nitrogen, but we can break it through vibrational excitation or more efficient than it was done in Haber-Bosch. We did plenty of experiments with laser spectroscopy. Here I will show just one example of what we did by use of the laser spectroscopy. We shoot laser through the discharge and we looked what is the fluorescence from different radicals and atoms, so we can know how they form, where they form, and how much of them is formed in the discharge. So here is an example of NO radicals kinetics, and what is already immediately visible that NO radicals appears, and the most intensive emission of NO fluorescence appears it's 60 microseconds after discharge. Discharge itself is only 10 nanoseconds. So discharge is somewhere here, and then it takes about 60 microseconds to form nitrogen oxides. And what is interesting there, that normally you would expect that nitrogen oxides will be formed somewhere right after the discharge. This is quite typical and classical what you see if you generate plasma between metal electrodes without presence of liquid. But in presence of liquid, what is happening, and this is what we proved from measurements of OH radicals, oxygen atoms, and NO radicals, what we proved is that actually effect of water presence leads to delay in NO formation, and NO is formed on a very long time after the discharge, because NO is formed because of these reactions, because of reaction of OH radicals, HO2 radicals, and also reaction of NH radicals with different species, and that leads to formation of NO. And if you look on kinetic of atomic oxygen in red, OH radicals in blue, and NO radicals in black, you can see that when OH radicals intensity drops down in the discharge, NO start to grow. So the main mechanism was what is called extended Deutsch mechanism. So NO radicals are formed because of the reaction with OH radicals. And so use of water in the discharge helps to change the chemical pathway, how we form OH, or how we form NO radicals. And that helped us to run the Deutsch mechanism. Was it energy efficient? Unfortunately not. So even with all what we did with this kind of discharge, we still got energy costs which were about 5 times higher than Haber-Bosch. And so if you try to compete with Haber-Bosch, if you are 5 times more energy demanding, there is no chance that you can do this process in the industry. And the main reason was that despite the fact that it's non-separate discharge, you still need to sparkle water, you still need to evaporate water, and all of this needs energy. And because of this, you're losing plenty of energy on those processes which are leading to water vapor evaporation in the gas phase, where this extended Dodge mechanism starts. So, at that moment, we were thinking about maybe we can do something different. Since we have water and we know that with the presence of water, we can change the pathway of chemical processes in nitrogen discharges. Maybe instead of use of plasma to make nitrogen oxides, we can use plasma directly to make reduction chemistry, so to produce ammonia, and basically to have ammonia production and then fertilizers. So the basic idea was that if you have oxidation process and we couple this with reduction process, we can have in the same reactor, we can have HNO3, ammonia, and then in one synthesis, we can perform fertilizers. So this would be the dream for industry. And this work we did with University of Antwerp, with group of anemic bogaerts, and the idea was following. We take a discharge, which is non-thermal plasma, we run it in a mixture of nitrogen with water, and we run it also in a mixture of air with water. In a mixture of nitrogen with water, we know that we can form ammonia. The question was if we can do it also in a mixture of air with water, because nitrogen is a rather expensive gas if you are speaking about large-scale production of fertilizers. It costs money, so you can replace it with air, and we can run this process, and we can form in one process nitrogen oxides and ammonia. Then we can have one-step fertilizers production. So very similar discharge where we have transient spark or low current arc, again pulse discharge in such configuration. We place this discharge above water. The reason to place it above water was not to change any chemistry because of the water layer underneath. That layer was used just to store the product, which are formed by plasma. And plasma was ignited either in a mixture of nitrogen and water or in a mixture of air with water. And the first results were immediately indicating that in nitrogen water mixture, we form nitrogen oxides and we form ammonia. So everything as is expected. However, as soon as we change from nitrogen into air, we don't see ammonia at all. Ammonia is a black line in FTIR spectroscopy, so we put products which are formed here into FTIR spectrometer, but we don't see ammonia. However, what was interesting for us, if you detect the emission spectrum of the discharge, we see that there is a peak of NH radicals. So if this is a spectrum of the discharge on different distance from the nozzle of the plasma, and we see this peak, this is representative of NH radicals, and those are formed only if there is ammonia in the discharge. So ammonia dissociated to produce NH radicals, and they give emission. So if we see the emission, there must be ammonia which is formed, but we don't see it in FTIR spectrum. So this is a spectrum, what we observe in FTIR spectrometer, nothing. But with spectra, emission spectra, we see presence of NH radicals. So the question was what is going on there and how we can improve it, how we can force this plasma to form stable ammonia. And the answer was rather simple. So what we did, we put a quenching solution. So immediately after the discharge, we put solution where we can quench this. And when we put this solution, before FTIR machine very close to the discharge, we start to see peaks of ammonia spectra. And the reason was rather simple. This is a process which is responsible for formation of NH4 and NO2, but this is an unstable product. And this product very fast will be decomposed into nitrogen and water. So we are forming this product in the gas phase. It immediately decomposed, and we don't see anything in the atmosphere. So if we quench it in a good way, then we can produce ammonia-containing products, which can be then oxidized to form fertilizers in a single step. So ammonia indeed can be synthesized in humid air plasma. However, it reacts and decomposes. We need to find a good way how to quench the products. And this could be the way how to produce in single step products which are useful for industry. However, this was one of the disadvantages This is a comparison of our results in terms of energy costs with literature. Honestly speaking, if you look at literature, there is no plasma process which is capable now to produce ammonia with energy costs. Either you need to go to low pressure microwave systems, but then you also think about low pressure, which is hard to transfer to industry, or if you think about atmospheric pressure, then energy costs are higher. In our case, the efficiency of ammonia production was about 1%. So if you compare with thermodynamic limit and Haber-Bosch thermodynamic limit, we are still very, very, very far away from the industrial demands. So the question would be to improve our system and also, of course, to somehow improve in general energy efficiency such process to reach industrial requirements for upscaling of such kind of processes. However, there are some conclusions. What we did from our work, that pulse discharges in presence of water can initiate nitrogen fixation. And we can do it by both oxidation pathway and reduction pathway. We can shift the chemical kinetics into extended cell damage mechanism. So we can push our plasma to either do oxygen-nitrogen chemistry or OH nitrogen chemistry. And by this, we can fix nitrogen, and we even can do formation of ammonia products. And however, the biggest challenge to solve is energy efficiency of nitrogen fixation. This is still not solved, and we are still working on this optimization of the system to reach higher energy costs, or to reach lower energy costs and higher energy efficiency. The second project, which is very close related to the previous one, was the use of plasma for gas reforming. And why it's very close related to the previous one, we will see immediately that reactor what we use is actually the same reactor that we use for nitrogen fixation. But the idea of this project, which was very successful, is still ongoing, have very good results in this project. The idea was following: if you have hydrocarbons, with methane or some other hydrocarbons, they can go to electrified rotor starter cracker. It's some kind of device which heat gas by electricity. You heat gas by electricity and you produce a mixture of heavy hydrocarbons. Then the mixture of heavy hydrocarbons also contains a lot of ethylene, and we send this mixture into plasma reactor. And in plasma reactor, we do two processes. We try to optimize it to highest as possible production of ethylene and acetylene. So what we need to get out of the reactor is a mixture of acetylene and ethylene. And then it goes to the plasma catalytic cell, where all acetylene is transferred to ethylene. So at the end, from hydrocarbons here, which could be butane or kind of mixture of different hydrocarbons, we want to obtain ethylene with as high selectivity as possible. And then ethylene can be used for multiple chemical processes. Ethylene is a first product for all kinds of polymer chemistry. So what we did, we used a nanosecond discharge where plasma was ignited between two electrodes. It looks very similar to what we have when we run plasma in between metal liquid electrode. Here, two electrodes are both metal electrodes. And we studied this kind of plasma from experimental point of view. So we looked at the kinetic of products which form. And we also looked at them from the modeling point of view, what are the pathways, how different products are formed. And in order to provide inputs for kinetic modeling, we need to give electron density, we need to know what is the gas heating, we need to know how much of energy spent for the heating, how much of energy spent for chemical processes. So the first what we did, we started by broadening what is happening with electrons, how electron density is involved in the discharge, and you can see the discharge has actually two peaks depending on the pressure in the reactor. We have the first peak which corresponds to the main pulse of the plasma, and then there is a second peak because power what we inject in the reactor will be reflected. Not all the power is consumed in one peak. Part of power will be reflected and will reignite plasma with some delay after the first pulse. This is what you see: the higher the pressure, the stronger the second peak is. But in all conditions, independent of the pressure which we studied process from 600 millibar up to 3 bar. So for all of them, we have electron density which is rising high. And surprisingly, when we looked at the ionization of plasma, that was in the range of about 10%. So we have really strongly ionized plasma in this kind of gas mixture, which was a mixture of methane with hydrogen. We also looked into what is happening not with electrons, but what is also happening with neutrons. How do we heat them? And then we found that depending on the pressure in the reactor, typically the temperature in the gas in between 3,000 degrees and something like 2,000 degrees, with a minimum in the range of about 2,000 degrees. But still, plasma is rising hot. And immediately the question was, because we see that the discharge is thermalized after the pulse, the question was how much of chemistry, what we initiate, is because of electrons, and how much of chemistry is because of the heating. To heat gas by plasma and to run chemistry of methane pyrolysis, that will be very, very energy efficient. You don't want to start chemistry because of the heating. You want to start chemistry because of the electron impact process. So our question was, do we really do that in this plasma, or we start everything by heating? And this is a scheme of all the processes which were involved in the modeling. And there you can see what is a thermal pathway, so how acetylene is formed because of the heating. But you also see what are different kinds of vibrational pathways and electron impact pathways. And in our plasma, we had a big question: do we start everything by electron impact reactions? Do we start everything by thermal processes? Or we have some kind of vibrational excitation which initiates also chemistry? To answer that, we looked in two products. One of them is hydrogen. So we did a time spectroscopy of hydrogen. We see how hydrogen is formed in the reaction pathway. Hydrogen is formed in every single step we formed hydrogen atoms. So they are very representative of the pathway of kinetic of methane reforming. And the second product is CH radical. CH radical is one of the last products in the whole chain of dissociation of methane. So CH is the final product before it breaks into carbon. And here is just an example of the tariff spectrum, how it looked like. And then we use this to calculate the density of atoms, of hydrogen atoms. And here you see kinetics of hydrogen atoms and kinetic of CH radicals after the pulse. And here are some numbers. So first of all, for CH radicals which are in blue, we only were able to detect them at very low pressure. So as soon as pressure reaches something like 200 millibar, we see very little of CH radicals. And if we go to atmospheric pressure, we don't see them at all. Or at least they are below sensitivity of our technique. And for hydrogen, we see rising high density of hydrogen. And if you compare this density of methane, you can see that methane is completely dissociated during its pulse. And since we know all of this, and this experimental data, we can do quite interesting study. We can run the simulation. And in the simulation, we can simulate what we do with the thermal chemistry. We know the temperature in the gas phase. We know how temperature is changing. If we put this in the simulation, we can see how much of methane will be dissociated and will transfer to different products because of the heating. And this is what we did. So here is a present results what we got from thermodynamic simulation of gas mixture. And we see that amount of hydrogen which is produced in the temperature range which we measure in our plasma. Only about 10% of hydrogen, if you compare with experiments, is formed because of the heating. So we can see that, yes, heating is important. Yes, heating runs partially the pyrolysis of methane, but it's not completely that we pyrolyze all the methane because of that heat. So there are two processes which are electron-driven. It's the electron impact process or vibrational excited processes which leads to formation of valuable products. This project is still ongoing. We also do now coupling of plasma reactor with catalyst, and we got right a good selectivity for the formation of ethylene. I hope I will be able to give the final results on the conference in the summer. And today I want to give just intermediate conclusions from this research, what we are still doing. So nanosecond discharge was applied for plasma to olefins. So we want to make from natural gas olefins. Based on the kinetics of short-living products, we see that they have 3 microsecond delay of decay time defined by chain reactions of methane decomposition, and gas heating contributes and substantially contributes to the chemistry, but it's not that all chemistry is defined by gas heating. There is a substantial amount of reactions, substantial amount of products which are formed because of electron and back processes. Of course, product yield, selectivity, and energy cost are still important aspects, and they need to be addressed. For instance, in our case, we are trying to address them by coupling of plasma with catalytic reform. And with this, I still want to go to the last, my favorite part of our research, what we are doing, and that is the use of non-thermal plasma for clinical services. This was exactly the project when I contacted with Krista for picosecond laser spectroscopy, and the project was related to investigation of non-contact cleaning of unstable semi-cultural heritage materials by plasma. And the basic idea was to find the way how we can clean the surface of very heat-sensitive materials without touching the surface. And all of this is linked to rising historical investigation and development in European Space Agency and NASA. And in both agencies, they are dealing with the use of atomic oxygen, and we study how atomic oxygen reacts with different materials. For them, it's very important because in the place where satellites are flying, so in the high orbit, amount of molecular oxygen is very limited. It's about 4%. And most of oxygen is present as atomic oxygen. And atomic oxygen has a feature. Atomic oxygen is reactive. It reacts with all kinds of organic materials. So typically what is happening with all organic polymers which are on the satellites, they're slowly decomposed. And it leads to failure of the satellites. And of course, in both ESA agency and NASA, they want to test atomic oxygen, and they have 2 facilities. One in ESA is called LSPM facility, where they produce oxygen at very low pressure chambers, but large volumes. Our approach was different. We want to produce atomic oxygen. We want to use atomic oxygen, which is produced in atmospheric pressure, to come to the surface and to clean the surface. For instance, if you have a surface which is coated with soot or some kind of organic particles, if atomic oxygen will come to the surface, it will mineralize all the organics, forming CO, CO2, and water. And the question was to find the way how to produce atomic oxygen very efficient and how to produce it in such a way that plasma, which is formed here, will not hit the gas. Because these materials, what you want to do, that show at the end, for examples, some materials are very heat sensitive. You cannot heat them even to 45 degrees because they will be damaged. So our strategy was rather simple. It's the use of helium-oxygen mixture. And we want to start radio frequency plasma. So this is the whole schematic of our plasma source. It's a low current radio frequency arc, which is ignited between 2 electrodes. And when you push a helium oxygen mixture to it, it will be ionized. Big amount of molecular oxygen will dissociate, forming atomic oxygen, and that can react with the surface, the material which replaces the needs of the discharge. There we have 3 strategies what we can do in order to increase the amount of atomic oxygen. One of them, we can play with gas composition, basically by adding molecular oxygen. Second one, we can enhance the transfer of atomic oxygen from plasma to the sample, for instance, with the use of shielding gas. And the last one, we also can control how much of atomic oxygen is produced by playing with radio frequency pulses and also by tailoring waveform of radio frequency. And all 3 strategies we are working on right now. And I will show you a couple of examples what we already achieved. And I will also show one of the case studies of the cleaning process. So this is a combination of nanosecond spectroscopy, what we do in Ghent, with picosecond spectroscopy, what we did here a couple of months ago. So what we basically did, we have an effluent of plasma, and we shoot laser through that effluent in different points, and we looked into fluorescence which could be calibrated, and then from this fluorescence patterns, we can get atomic oxygen density. And then, if we know atomic oxygen density, we can try to play with plasma parameters to optimize the system to get the highest production of atomic oxygen without heating the gas. Here is an example of what is happening when we start to play with power. So when we increase power, obviously, atomic oxygen density goes up. Here, as you can see, the signal is not yet calibrated. So the signal here is in arbitrary units. We are working on the calibration process for this experiment. And it still gives an idea about what is happening when we increase the power. So the density of atomic oxygen is increasing. Why we stop at 10 watts? Because this was the maximum power where we still can get plasma of relatively low temperature. Also, what we did, we replaced with the amount of oxygen, molecular oxygen, which is added in the plasma. And there you have two processes. One is that you produce more atomic oxygen, but at a certain moment, and you can see it, when we increase the amount of molecular oxygen too high, we start to produce ozone. And ozone is not it's not the best product to have when we treat cultural heritage objects. Ozone will go to the surface, will stay on the surface a day, a week, a month, and will slowly oxidize the surface. So you can finish the treatment, everything is fine, and then the surface turns from white to yellow in a matter of weeks or months. And if you treat the paint and then paint, you change the color, this is a big problem. We want to have a plasma treatment which, when we stop it, everything stops. There are no radicals anymore on the surface. There are no stable products on the surface like ozone or hydrogen peroxide or whatever. We want to have those products which are short-living, and they only live when plasma is. Which means that you can increase the amount of molecular oxygen, but you are limited by the way how you optimize your system for the high production of atomic oxygen. You cannot go too high because you start to produce unrecyclable products like ozone. This is what we see at highest concentration of molecular oxygen. And then we looked into effect of harmonics. So what we did, we have a main frequency, what is used to ignite the plasma, 13.56 megahertz, and then we start to add harmonics. Second harmonic, third harmonic, and so on. By tailoring the voltage waveform, we know that we can change somehow electron energy distribution function in the plasma, and so we can change the amount of atomic oxygen which is produced without the heating. And here are the first results, and they don't look remarkable, but still there is an increase by about almost factor of 2 from what we have when we are working with fundamental harmonic and what we have when we have the same power, but we start with the second harmonic to the first one, and we also play with the phase shift between two. And by optimizing the phase shift and amount of harmonics what we introduced, so basically by tailoring the voltage waveform, we can increase concentration of atomic oxygen in the effluent without changing the gas temperature. And so with all parameters which are optimized at the moment, as what we have at the moment, we start to work on one case study. We are trying to develop the best possible technique to remove soot. Soot is this kind of small dark particles which are formed when candle is burned or when there is a fire, when for instance was devastating destruction in Notre Dame. Have even samples from Notre Dame de Paris, where people are looking how to remove the soot. Because you can't use solvents. Soot is a tiny particle, you put solvent, soot will be partially dissolved and it will go inside of pores of materials and you will never take it out. You cannot use laser ablation. There are problems with that because typical wavelengths of the laser is not suitable to remove soot. So there are basically no techniques to remove soot from most of material except of stones and some kind of very hard materials. You can do it in a mechanical way. And here I hope I can show. Can you maybe click on the video? I don't know if it will work. This is a typical example of what we have when we are using plasma for the cleaning of the materials. So plasma is formed inside of the jet. There is no effluent which is visible. What is only is the effluent is atomic oxygen. Atomic oxygen goes to the surface of the material and can remove ash from the surface without damaging the material. Here you have an example of plaster. So this is what is pristine plaster look like. Then we soot it in different conditions at different temperatures, and then we clean it. And this one looks almost the same as the beginning, as the pristine one. And even more, if we do that on textile material, you cover this, and then you remove from textile suit, you still can see some features on the textile material which were present in the initial virgin material before suiting. So we really can find the conditions where we can sensitive enough to remove all the top layer of soot without destroying anything on the material, including the fibers. So these are fibers, how they look like before the soot. This is when they are suited, and this is when they are removed from the cotton. And there was no damage after the atomic oxygen cleaning. We are still tuning parameters of our cleaning system, and now we have several parties working on different case studies, so that they are doing different treatment of different materials, even very soft materials, very heat-sensitive materials. So we are trying to find the limits of this technique and to what extent it can be used, and what kind of materials is still applicable or not applicable. So with this, I go to the last conclusions from the part 3. So non-thermal plasma can be utilized as a source of atomic oxygen for very demanding field of cultural heritage. Atomic oxygen provide opportunities to treat very fragile and even porous materials, which only couldn't be used during the treatment by wet and dry cleaning methods. It's safe for the health. You don't produce anything except of CO2 and water. And what was also important, and this was unexpected from the beginning of the project, people who are working in cultural heritage areas are very resistant against of anything new what you propose to them. Like laser ablation, it took about 20 years for people to convince that laser ablation can be used for some specific cases in cultural heritage area. But with atomic oxygen, they were quite happy to work with this because they're considering that atomic oxygen is produced from mixture of helium oxygen, so it was some kind of natural product for them. So they are now using our machine in different locations, and we hope to get very new case studies for the future from them. So in here, all the conclusions and future outlooks, I will not go through them, I will go to the last one. Our research unit, plasma technology, is interested to cooperate with everyone, and we are particularly interested in plasma surface interactions, in the design of plasma sources, and the diagnostics of plasma, and also reactive oxygen nitrogen species. And with this, I would like to thank also all the people who were involved with me in 3 projects that I showed today. So this is our team, but also there are other people who are involved together with PhD students, former PhD students, the ones who are now working with all of us. And so, thanks a lot.
Thank you very much, Anton, for the excellent presentation. I think it was a really nice overview of the work you realized in many interesting applications. Also, diagnostics and modeling to couple and to understand reaction kinetics, thermal mechanisms, and so on. So now the floor is open for questions. I would invite the first people from the room, if they have questions to ask. People online, either they can write in the chat or they can open their microphone to answer afterwards. Yes,
thank you very much for this very nice presentation. Also, many questions in that, but basically, I have maybe two main questions. The first one is for natural fixation. Basically, the figures you showed basically indicate that we are very far from, let's say, the thermodynamic equilibrium for NH3 and say basically it's not only optimization, we have to really very large efforts. If I understand well, what you it's not about optimization, it's really we are very far.
very clear.
I didn't show a table here, but I also had a table in my presentation, which I prepared from the beginning. And very remarkable that now we are 100 years after first plasma process, which was used to produce nitrogen oxides. And their energy cost was about 2.5 megajoule per mole. And if you look in the literature, very little of groups can reach even that number, 2.5 megajoule per mole. and Haber Bosch is 0.5 megajoule per mole. So we are indeed very far from that metric. There is one possibility how this kind of plasma process can be, I would say, sold to industry. One of the ideas is that you can run plasma process on very small scale. So basically, you can place plasma device in the place where there is a free electricity. You can produce fertilizers, even if it's much more expensive than Haber Bosch. But you can produce it in place where you can produce it in greenhouse on your demands. And by this way, you can somehow solve the problem that plasma is still much more energy demanding in relation to Haber Bosch. But at the moment, indeed, it seems that whatever we are trying, if we are at atmospheric pressure, it's very difficult to run this process by vibrational excitation and to reach thermodynamic equilibrium or to beat thermodynamic equilibrium. We are still, I would say, much worse in relation to Haber Bosch. That is all.
So thank you in any case for showing the limitation, because many speakers show the possibility of plasma, but they don't insist on the limitation. Thank you for this. Really, your presentation was clear. And basically, why don't they think to, for example, plasma catalysis in this case? Are there any efforts on plasma catalysis?
Yeah. So, okay. Rate of work on plasma catalysis is one of the big issues with plasma catalysis. That if you do it in situ, so you put catalysis in the plasma, of course, catalysis will be affected by plasma itself. So the lifetime for catalysis is rather short. And this is what you need also to deal with, and you need to find the best catalyst. And there are plenty of groups working on plasma catalytic process. So this may be one of the way to go, and maybe this would somehow will be competitive with Haber Bosch.
I have maybe said a question.
Yes.
Just on the last topic. In fact, a long time ago, we worked on diesel soot oxidation by plasma. In fact, we really struggled on these topics because, in fact, what we found is that when you send oxygen, but also ozone, kind of mix of oxide, in fact, you oxide, but you end up with a complex, when you have real soot, not black carbon, real soot, PAH with polyaromatic hydrocarbons. You end up forming some groups, and you cannot dissolve. But basically, you oxide, but you stay on the surface, you stick to the surface. And then it's very hard to explain. The only way we found at that time was to heat. And I really was surprised for this result where you can oxide, basically, you make the chemistry, but you can also dissolve the product. And this was really surprising to me, in fact. So maybe the discharge configuration is different.
There was something interesting, and this was from the beginning of the project. So the first soot, what we got, it was soot. You can buy it. You can buy soot from different companies.
Yes.
And many of them are producing soot in the way that it should be representative of real soot, which is technically doing fire damage. Because we also have mock-ups materials which are with soot, which is natural soot, which is because of the fire. And we found out that even without plasma, with this long treatment time, you can remove many compounds which are commercially available. And then we start to look what the soot is there. And very often they are using graphite or some kind of graphite-based materials, which they make as a powder. They mix with hydrocarbons, with polyaromatic hydrocarbons. And then what is happening, polyaromatics we can remove. So it's quite easy to mineralize and fully oxidize. With graphite, it takes very long time to oxidize it. And so then we see that many commercial products are not actually representative of soot, which is during the fire damage. And now we have a facility to make this fire damage mock-ups. And on those ones, and this is what I showed today, on those ones, atomic oxygen works very well. You also found out that if you increase the amount of molecular oxygen, so we start to produce ozone waste, doesn't do anything good. So what you do on the surface, you are forming some epoxy groups on polyaromatics.
Yes, exactly.
And those epoxy
Exactly.
basically somehow blue.
Yeah, exactly. This is what we found.
Yeah, and then after the treatment, if you do it wrongly, you even with solvents you cannot remove.
This is exactly what we have. Because we have to put this on the exhaust of the cars. So we cannot put helium. Yeah, and exactly, this is exactly what happens. But in any case, thank you very much for the presentation.
Thank you, Khalid. Is there any other question?
Thank you very much, Anton, for the very nice presentation. I have a technical question because I have run to a similar thing, and when I saw this in your presentation, it popped in my mind. At some point, you show a spectrum of the N2 band, and you have some overlapping from the NH molecular band. Exactly. I have a question here. How do you fit this cumulatively to analyze the spectrum to determine temperature?
So for the temperature, we use, I didn't show this today, we use a rate scatter.
Okay.
So we didn't simulate the spectra in order to get the temperature. Because the problem with nanosecond discharge, there are two problems. One problem is that indeed you have NH, which will overlap with your N237 line, but this is not the main problem. The main problem, because it's a nanosecond discharge, there is quite a lot of sputtering of the metal electrode. And that sputtering leads to formation of some kind of continuum background in the spectra. So this was the second problem what we deal with. So simulation of that spectra and modeling of the spectra, you can do it. You can try to do it by limiting your simulation part only for beginning of the band in the head. But we decided to use radio scattering. So we shoot laser with 532 for the plasma. We look into radio emission, and that gives you directly measurement of gas temperature. And this was the easiest for us to do. That is very difficult to do for methane plasma. In methane plasma, you have formation of soot, and then your laser, what you shoot through the plasma, will irradiate because of the new scattering, and so radio scattering will be not the dominant. But in this kind of plasma, no problem. You shoot the radio, you shoot 532 for the plasma, you look for the radio scattering, and you can get the temperature. This is what we did.
Any other questions? Yes.
Thank you very much for your presentation. First, technical question. What is the maximum oxygen you use for cleansing process in your plasma?
For cleaning. For cleaning, you mean?
Yeah.
We found out that the optimum was 0.50% volume percent of oxygen.
0.5.
No, 0.15. 0.58. This was the maximum, this was the optimum. Yeah. If you go higher, at 0.3, you have a high amount of atomic oxygen, but plasma is heated up. At 0.4%, we have a lot of volume oxygen. And so the optimum was 0.50.
The second question, and last one, did you use during the production of ammonia? Aperçu process industrially is based mainly on the catalytic activity of platinum.
Yeah.
Did you use platinum in this case to accelerate your reaction?
No. So the reason for this work was to find if we, in principle, if we can form ammonia in the mixture of air and water. So we didn't look for plasma catalytic process. We only want to show that ammonia can be formed in the plasma. To increase the amount of ammonia which is formed by presence of the catalyst, this is something what we did do. I know the group of Anton Nikiforov, they are now working on this, and they are trying also to develop model to include the plasma catalytic processes in the formation of ammonia. But experimentally we didn't do that.
We used in the past water as an oxidant in the plasma. But here at study we used it as a reductor agent.
In previous here in this work, water was used as oxidizer.
Yeah.
So here we produce nitrogen oxides. And energy efficiency of oxidation pathway was much higher than energy efficiency to produce ammonia. Still worse in comparing with Haber-Bosch, but this was much more energy efficient in comparing with ammonia production. And here water was used only as.
So in reaction, water has a reductive action.
Yes, but you need to force water to form hydrogen and to react with the formation of ammonia. So in most of cases, in nanosecond discharge with liquid electrode, for instance, where concentration in water is very high, then we only see oxidative processes.
Depends on concentration.
Depends on the concentration, because here we are speaking about 20% of water, and here we are speaking about 0.01, 0.1% of water only. So it's really very different amount of water what we use.
There's a question from
I have one question. What is interesting about your methane work? We are also working on methane here. Do you find some nanoparticles or particles in your plasma? Because we find a lot of particles.
This is our experimental nightmare. So, wait, I want to show tariff experiment. Yeah, tariff. All what you see around, all of this around, it's nothing else but emission of salt.
It's a soup.
Yeah. So even with tariff experiments, we can run them. If you can see, we start from 2 microseconds from the discharge, because we start to have a hydrogen, but we need to finish about 30 microseconds after the discharge. Why? Because at this moment of time, soot starts to form. And then soot is so illuminating, so strong that basically you can even see the laser beam passing in the reactor because of the soot. And we are trying to solve this. We are also playing with a mixing of, at the moment, of CO2. We also did a mixing of nitrogen. But of course, for experimental work, it's interesting. But from industrial point of view, you want to work with pure hydrocarbons. The formation of soot is really a problem. This is what we also have. And now we are moving to heavy hydrocarbons like styrene, which we also want to decompose by the same process. And we not only have a formation of soot in the reactor here, but it also starts to form some kind of wires, I would say, from one electrode, and in a matter of half an hour, it reaches the second electrode. So it's some kind of tiny filament of carbon, which goes between 2 electrodes, and basically then it makes a short arc between electrodes. This is another problem that we have to solve. So it's difficult.
When you characterize the material, is it graphitic or silver?
We try graphite as electrodes. We try nickel as electrodes to prevent formation of this black carbon or this amorphous carbon material. And then we also looked at how variable is this material. So there are people in the University of Gand, they are our partners in this project. So they are looking if material, this carbon or soot, is variable. And up to now, we see that it contains a lot of amorphous carbons, which is not what we want as a variable product. We want to have nanomaterials like nanofibers or carbon nanotubes. But here, in the reactor as it is now, we are forming basically ends. Very difficult to get selective deformation of fullerenes. Yes, they are present in the deposit, which is formed here in the reactor, but large quantities is amorphous carbon, graphite, you have nanodiamonds, you have basically everything.
Is there any other question from the room? No. For the people online, is there any question? Okay, so there is one question from Alex. Thank you very much for the nice presentation. My question relates to the last part of your talk. Do you consider soot after or during plasma treatment? What does it become, and do you care? And does it affect the plasma? Is the plasma chemistry and treatment efficiency affected over time during treatment, for instance?
So I will start from the last part. Formation of gaseous products doesn't influence plasma. The plasma itself, if we go back, can you go back to presentation?
Yes, sorry.
So if you go present. The plasma itself is formed inside of the nozzle. And then there's a flow of gas about 3 liters per minute, blowing all the plasma products to downstream. And the products which are formed below the plasma surface do not affect the plasma. We don't see any substantial changes on plasma parameters when we introduce the substrate. Yes, there are very tiny changes on the temperature of gas, because of the changes of the gas flow dynamic, but not something substantial what we see. From the products, so far we are working on measurements of the products with FTIR. Right now there is an experiment ongoing in Eindhoven University with mass spectroscopy. The only products what we can see are CO2, water, and CO. Primary is CO2 with small amounts of CO. Depending on what kind of soot is used, the amount of CO can be a little bit higher, a little bit lower, but still it's something like 10% of the total production of CO2. We don't see any other byproducts, or we don't see any kind of heavy oxidized compounds which are formed, but we are working on that. We are trying to understand if we partially oxidize soot, what is formed there? Do we oxidize it, or we do like a complete mineralization immediately? This is still open question. We are trying to work on this. And this project is only run for 2 years. So we hope to get a full picture of oxidation pathway by the end of the project. But indeed, it's a question what we want to answer as well.
Okay. I think, is there any other question from people online? So if not, I think it's already time to lunch, go to lunch. Let's thank Anton again for the excellent presentation. And have a nice day, everybody.
Thanks everyone, and just
Thank you very much.
see the last message. We are very open to collaboration.